So now let's look at some of the groups or families on the periodic table in a little more detail. The first group we're going to look at is group number 1. Group number 1 is known as the alkali metals. And they are group 1. Now, what do all of these elements in this column have in common? Well, the first thing and most obvious thing when you work with these metals is that they are the most reactive of the metals. So these are the most reactive metals that there are. And the reason for this is they only have one valence electron. And when they react, they're going to get rid of that electron. So these elements, they have one valence electron. So for example, let's take sodium. Sodium has one valence electron. It's very easy for that sodium to give up that electron and become sodium with a positive 1 charge, which is much more stable. So these are so reactive. They are the most reactive of all the metals. What else do these metals have in common? Well, surprisingly, they're actually soft. They're actually so soft that they can be cut using a knife. Almost like butter. They're very, very soft metals. Additionally, because they are so reactive, they are never found alone in nature. And what I mean by that is that they are always bonded, or chemically bonded, to another element. If you had a large block of an alkali metal just sitting out in the environment, right away it's going to start reacting with water, with oxygen in the air, with the things around it. So you won't find pure lithium or sodium or potassium or cesium just alone in nature. And in this image, I have some of the alkali metals. So here's lithium. Here is actually sodium. So this natrium is this is from a website that is not written in English. So this is what we know of as sodium. And then we have potassium, rubidium, and cesium. Now notice that they're all kept in very special containers. Both lithium and sodium are actually kept under oil. These metals are so reactive that they'll react with water, even explode when placed in water. So we can't keep them in water, but we keep them under this special oil in order to prevent them from reacting with the air, because they will react with the oxygen in the air. Potassium, rubidium, and cesium are even more reactive than that. So therefore we have to keep them in these sealed glass containers. So the only way to get them out of these is to actually break the containers, and they're usually filled with some inert gas, some unreactive gas to keep other types of air, oxygen, from getting inside. The second group that we're going to talk about is group number 2. These are called the alkaline earth metals. And these are, again, group 2 on the periodic table. Now, what properties do these metals have? Well, like the alkali metals, they are very reactive. But they're not as reactive as group 1. And the reason for this is that they have 2 valence electrons. So if I draw the Lewis structure, say for calcium, it has 2 valence electrons, so it would have to get rid of both of those electrons getting a +2 charge in order to become stable when it reacts. So getting rid of 2 electrons is not very hard to do, but it will take longer than something with only 1 valence electron to get rid of. Therefore, they react much more slowly. But as we can see in this image, so I have a bunch of alkaline earth metals listed here. Notice how they have a shiny look to them, but some of them are darker. Well, what is that dark color on them? Well, that's actually an oxide, meaning on the surface, because these metals have been exposed to the air, they react with oxygen to form what's called an oxide. Beryllium oxide, magnesium oxide, calcium oxide. It's actually a form of salt. And if you also look, these two, the strontium and barium, are even more reactive than these. Beryllium, magnesium, and calcium can actually be left out in the air for short periods of time without becoming too reacted. But these must be contained in either some kind of oil or a sealed glass tube because they're even more reactive than the first few alkaline earth metals. And because they are so reactive, they are also never found unbonded or unreacted in nature. Or they are never found pure in nature. So if we want pure calcium, we actually have to do a couple of different chemical techniques in order to separate it. One other thing I would like to point out with these is calcium. Well, calcium, we tend to think of bones and teeth when we think of calcium, but notice that pure calcium is actually a metal. It has the properties of metal, which means the calcium that's in your body is bonded to other atoms and other molecules, which gives it that white kind of look that we think of when we think of bone and teeth. But pure calcium is a metal. Now let's look at the biggest group of metals, and these metals are in the center and a little bit into the right side of the periodic table, and they compose groups 3 through 13. These metals are known as the transition metals, and they are groups 3 through 13, and as you can see, boron is not included in the transition metals. Well, what do these look like? Well, transition metals are actually the metals that you are probably most familiar with. Copper, silver, gold, mercury, platinum. We also have zinc and tin and titanium. Those are all transition metals. So they have the properties that you usually associate with the metals. They're shiny. They're not very reactive. Some are more reactive than others. And most interestingly, when you react these metals with another compound, such as oxygen or chromate or nitrate, something like that, and dissolve them in water, you get these really vibrant colors. Transition metals are used to make paints and other things that need to be brightly colored. So transition metals form compounds that are very colorful, especially when dissolved in water. And as I said, some are reactive and some are very stable. And this has to do with how we can't actually predict the number of valence electrons that these elements have, so they're going to have different properties. For example, metals like silver and gold, copper, and zinc are very unreactive. This is why we make a lot of coins out of copper and zinc. You wouldn't want your coins reacting or dissolving in your pocket. We don't use metals like iron or chromium in these types of objects, because if you had an iron coin, think about what iron does. It rusts. It reacts with oxygen. So if you made a coin out of iron, it would very, very quickly rust because it reacts with the oxygen in the air. So most of our elements on the periodic table are in the transition metals. Now let's move to the nonmetals. So we said, well, most of this column, with the exception of boron, is a transition metal. Boron is going to be a metalloid. Now let's go to the next column, this carbon family. We can't say much about this family as a whole because we have a nonmetal and we have metalloids and we have transition metals. The same thing is true about the nitrogen family or nitrogen group. We have metalloids, metals, and nonmetals in this group, so their properties do vary. All we know is that they have the same number of valence electrons. Lastly, the oxygen family, also, we can say they have the same number of valence electrons, but we have nonmetals, metalloids, and metals, so we're not going to be able to say much about the groups as a whole. What we can talk about, though, is this second to last column, group 17. This group is known as the halogens. And these nonmetals are the nonmetal equivalent of the alkali metals, meaning these are the most reactive of the nonmetals. So all of the elements in this group are very, very reactive. And the reason for this is that they have 7 valence electrons. So if I look at chlorine, chlorine has 7 valence electrons around it. That means it only needs 1 more valence electron in order to complete its octet. And in this case, like all nonmetals, it'll become negatively charged. So all of these elements in the halogens are very, very reactive. And they usually take the electrons that they need to complete the octet from metals which want to lose electrons, thereby completing their octets. So these halogens are very, very reactive. And like the alkali metals, because they are so reactive, they are never found in nature without a bond to another element. Lastly, and one of the most interesting things about this group, this is the only group on the periodic table that contains elements in all 3 phases. So, for example, fluorine and chlorine are gases. So here is chlorine gas, a sealed container of chlorine gas. Bromine is a liquid. It's one of the only 2 liquids on the periodic table. The other one at room temperature is mercury. And it has solids, like iodine and astatine. And here is iodine. It's a solid. The last group that we have on the periodic table is group 18. These are known as the noble gases, or the inert gases. Well, why are they called the noble gases or the inert gases? Well, all of these elements in this last column are inert or very unreactive. They do not react with any other element on the periodic table. So why are these elements so stable? Why don't they react? Well, we have to look back at valence electrons. These elements have a complete octet and therefore will not gain or lose electrons. They are already stable. So these elements, they sit alone. They don't interact with all the common folk elements. That's why they're the noble gases. Think of them like the king or the queen who doesn't want to interact with the rest of the people. And all the elements want to be like them. If you think about it, all elements want a complete octet, just like all of the elements on the noble gases. So the noble gases are very unreactive. But just because they're unreactive doesn't mean that these elements are useless to us. They have many different purposes. For example, when electricity is passed through tubes of these gases begin to glow. If you've ever heard of neon signs, now you know a use of a noble gas. Neon, when you pass electricity through it, glows bright red. Now, when no electricity flows through these gases, they're clear. You can't see them. They just look like your normal air. But once we pass through electricity through them, we get these really bright colors. The other thing that they're used for is to preserve important things. For example, the Declaration of Independence is kept in a sealed glass case. And this case is filled with argon gas. Well, why is this case filled with argon instead of just normal air? Well, normal air, what we breathe every day, contains nitrogen and oxygen and other gases that can react with the paper. So we fill it with argon gas because we know argon, being a noble gas, is not going to react with any of the molecules in the paper. If there was a chemical reaction with the paper, it would ruin the document. The last two groups of the periodic table that we'll talk about, now they're actually the last two periods we're going to talk about because they're the rows of the periodic table are the lanthanides and the actinides. Now these are also known, as it says up here, as the lanthanoids and actinoids, but the lanthanides are the first row of the F block, and the actinides are the second row of the F block. And in this image, I've put several pictures of different lanthanides, and all you really need to know about all of these elements, the lanthanides and the actinides, is that they are all radioactive, and some of them are naturally occurring, while others are made by humans. For example, uranium occurs naturally in the ground, so it's fairly easy to find some uranium all around you in the earth. But others, like americium, has to be made by humans. It does not exist naturally. And actually, this is the only human-made element that is found in your house. Americium is actually used in smoke detectors. Well, that's about it for the groups of the periodic table. And I know this was a longer video, but I hope you recognize that all this information that I gave you is on the periodic table. So this periodic table is not just a list of all the elements. It actually can teach us a lot about an element just by where it falls on the table.